Okay, these are your acid and base titration. Oopsie, here you go, titration notes. And this word here is titration. And the definition of this is essentially we're mixing an acid and a base where we are trying to neutralize the acid or the base to figure out the concentration, or what you know as the molarity. Okay, so what I've got written up here is a neutralization reaction between an acid and a base. I've done it in different colors here. Remember, this orange is your double displacement reaction where you mix an acid and a base. You always get some sort of salt and water, H2O. I've also just put in a different color here to make it more noticeable. Neutralization, to neutralize, to kind of bring to not acidic or not basic. We want the moles of the acid to equal the moles of the base. That's going to come into play in step 2. But remember, we are equaling out moles. This image here is going to show kind of how we do it and the tools we use. This big thing here is called a burette, and we're going to say the base in the burette. So we're always going to put base in burette. And it's 2 T's with an E because it's nice and French. So we have the burette with the base, and then we have an Erlenmeyer flask here with an acid, and also the indicator, because the indicator is going to change color based on acidic or base level. Think about, remember when we did the lab and we mixed phenolphthalein, it got really pink in the base, but it didn't do anything in the acid. That phenolphthalein shows us if the solution is acidic or basic. Here's another image kind of showing you what goes on. So if we have our base, remember our hydroxide ions here, and we have our hydronium ions here with our acid, the pH is below 7. I know we haven't talked about pH much, but 7 equals neutral. And then we slowly add base to it until the pH rises, and then when the pH gets to 7, we know we are at a neutralization. And when we show you in the lab, if you go too far, it's pretty easy to tell. Okay, so your paper has 3 steps here. And we have this example. We have 10 milliliters of hydrochloric acid with an unknown molarity, which is the big M. We don't know the concentration. We do know that it takes 15 milliliters of 3 molar sulfuric acid to neutralize that hydrochloric acid. So what is the concentration? Our first step is going to be to discover the known. So I'm going to circle in purple. I know 3 molar sulfuric acid. I know the volume of that. Circle those or square those or however it wants to help you. So I know 2 things about sulfuric acid, and I know hydrochloric acid is 10 milliliters, but I do not know the molarity. So I'm going to start with my sulfuric acid. The first step, and I'll write it for you a second, the first step is calculate what you know. Calculate your known moles. So I know that I have 3 molar sulfuric acid, which what I know about molarity, that big M really means 3 moles per 1 liter. However, I also know this 1 liter, I don't have my volume in liters. My volume is in milliliters. So I want to change this liter into milliliters. So what I do there is I multiply this 1 liter over 1,000 milliliters. These guys will equal each other, so really I'm multiplying by 1. What that does for me is I get to cross out liters, and now I have moles per milliliter. Next step, I multiply by my volume, which is 15.0 milliliters. Alright, and what that helps me do is cross out the milliliters, and what I'm left with is moles H2SO4. And so I know in 3 molar H2SO4, 15 milliliters of it, I have a certain amount of moles, which we'll calculate right here. Okay, so I multiply 3 by 1 by 15, and then divide by 1 and divide by 1,000. That gives me 0.045 moles of H2SO4. Actually, I'm going to put another 0 there to keep my sig figs correct. Okay, and so I know that I have 0.05 moles H2SO4. So now let's go to my second step. So here we use, the second step is use stoichiometry to find the amount of moles needed to neutralize. And I left neutralize there blank because right now we have moles of acid, and I just realized we made a mistake. We have acid and acid, so we're going to do this really quickly. Take a pen, cross out HCl, put in NaOH. There we have, my fault. We had an acid and acid, that wouldn't work. So now we have an acid in sulfuric acid, and we have a base in sodium hydroxide. Okay, so now we know the moles amount of acid that we have. Now let's find out the amount of moles base needed to cancel out that mole of acid. First thing we have to do, we're using stoichiometry, we need a balanced equation. So we start here, sulfuric acid plus NaOH, again, sorry about that. So this is a double displacement reaction where the cations switch. Alright, and so we're going to end up with Na2SO4, that's our salt, and H2O. Now looking at this, we make sure we have it balanced. I've got 2 sodiums here, so I'm going to need 2 sodiums over here. Let's put a 2 there. I've got 2 hydrogens here, plus a 3rd hydrogen here. Okay, and I only have 2 over here, so we'll deal with that in a second. Oh, excuse me, 2 here plus 1 times 2. So I've got 4 hydrogens on this side, 2 over here, so I can put a 2 right here. That gives me 4 hydrogens. 1 SO4, 1 SO4, again 2 sodiums, and OH comes in here, 1 O, and the H's are taken care of before. That is our balanced equation. Now we're going to use that balanced equation, and we're going to start with what we know, which is this here, moles H2SO4. So we're going to start H2SO4, and we're going to go to moles base needed to equalize. So we've got our starting point here, where we have moles H2SO4, and we want to get to moles sodium hydroxide. And so we have to use our mole ratio. I've got 2 moles sodium hydroxide, this big 2 here, for 1 mole sulfuric acid. Okay, so just multiply across the top, multiply that by 2, and divide by 1. And what it tells me is I need 0.0900 moles sodium hydroxide to balance out 0.045 moles sulfuric acid. So these first 2 steps, I know I have 0.045 moles sulfuric acid, and then I just calculated to balance out this much acid, I need 0.0900 moles sodium hydroxide. So now I have the molarity sodium hydroxide, or excuse me, the moles, and I have a volume. So my third step is going to be use moles and known volume to determine concentration. So again, I'm using the calculated moles and the volume to determine our unknown concentration, which up here is sodium hydroxide. So I know I have 0.0900 moles sodium hydroxide. That's what I got in step 2. What I also know from my directions is I have 10 milliliters of it. So in my 10 milliliters, I have 0.09 moles. Molarity is moles per liter. So to get this to liters, I want to, again, use stoichiometry or dimensional analysis to get my milliliters into liters. I know 1,000 milliliters is equal to 1 liter, and so that can help me cross out the milliliters and leave me with moles per liter, which equals molarity. And when I do this calculation, 0.09 times 1,000, don't forget to divide by 10. A lot of people forget to come back and do that division by 10. Yeah, I have 9 molar sodium hydroxide, which is pretty intense. Okay, so again, I calculated what I knew. I've got a volume and a molarity that helped me figure out the moles. Then I use those moles and my equation skills to calculate how many moles I needed to balance or neutralize. And then I took this mole calculation and my known starting amount, my base, and I then calculated the concentration of my base. Those are our 3 steps. Every titration calculation is going to look like those 3 steps right there. When we're actually doing the titration, you're going to drop in, and the phenolphthalein, when you hit it a little bit, the phenolphthalein is going to show up down here. And then what you're going to do is it says swirl. You swirl it around, and so you drop in slowly, swirl, and that pink color will go away. And what you want to do is when it starts to stay sort of light pink like this, you want to go almost 1 drop at a time, because believe it or not, we'll show you, we'll see it, just 1 drop can make it go from a light pink right here to a very dark pink, and then that will not go away. And that will let us know, okay, between this drop and this drop is when we went from more acidic to moles canceled out, and we got towards a basic solution.